Hello and welcome to our next lesson. This lesson is actually going to be a bit of a longer series. It's kind of like part 2 of Unit 1. The good news is that there's nothing really new that we're going to do in this lesson with a few exceptions. This is all going to be grade 10 review again. So what we're going to be looking at now is we are going to be looking at naming compounds. We now understand the different types of compounds. We've looked at polar covalent, nonpolar covalent, ionic. We understand how to draw those compounds. The next thing to know is how to name them. Naming is really the base of chemistry. So after this lesson, I'm going to go ahead and assume that you know how to name things. If you don't understand naming, it's going to be a challenge. So we're going to spend some time on it. So it is going to be a bit of a longer lesson. Before we get into naming, I just want to remind you a little bit of those chemical bonds. Chemical bond is a force that holds atoms together in a compound. So that's actually what we're going to be looking at now, is naming compounds. A compound is a substance that's composed of two or more elements chemically joined together in fixed proportions. So we're going to be looking at naming compounds, different groups of atoms joined together in fixed proportions. Now, what does fixed proportion mean? It means that when you're telling me a compound, it's not enough to actually tell me what's in that compound. So for example, when I ask you what the chemical formula for water is, you can't tell me that water is made up of hydrogen and oxygen. That's not enough information. When you give me the chemical formula of water, you have to tell me that is H2O. The reason that you have to tell me it's H2O, because there's other combinations of hydrogen and oxygen. So for example, H2O2 is hydrogen peroxide. So H2O2 has an extra oxygen on it. Hydrogen peroxide looks just like water, but if you drink it, very, very toxic and very poisonous, depending on the concentration. So it's important to not only tell us what's in the substance, but it's also important to tell us the fixed proportions, and we communicate that using these numbers here. We actually separate out compounds by bond type. So we're going to name things differently depending on what bond type they have. We've already looked at these bond types. I'm just going to remind you what they are right now. So our two bond types are, we have ionic bonds. We know ionic bonds have the exchange of electrons. So essentially what's going to happen is one atom is going to gain, the other is going to lose an electron. That's going to make one positive. That's going to make one negative. So essentially, that's going to form what we call an electrostatic attraction. So we're going to have one positive, one negative that are attracted together. Ionic bonds form when there's a really big difference in electronegativity. The difference has to be greater than 1.7. So examples of ionic bonds, here we have NaCl, that's sodium chloride. Here we have MgI2, magnesium iodide. We know they're ionic compounds one of two ways, either the electronegativity difference of greater than 1.7, or their ionic compounds are always metals and nonmetals. So for example, sodium chloride, sodium is a metal, chlorine's a nonmetal. Magnesium chloride, magnesium's a metal, iodine's a nonmetal, and so on. Let's take a look at our next bond type then, and our next bond type is covalent bonds. So covalent bonds are formed by the sharing of electrons. So they've got a smaller electronegativity difference. It means that it's not big enough to actually exchange electrons. Instead, we share electrons. So it's between two non-metallic atoms that have a similar electronegativity, and generally it forms when the electronegativity difference is equal to or less than 1.7. So some examples of covalent compounds that you might have seen, we have CO2, that's carbon dioxide, or CO, carbon monoxide. So again, you can see the idea of fixed proportions comes back into play, where the number of atoms that we have actually matters. So it matters if we have two oxygens or one oxygen. Carbon monoxide, again, very, very toxic. Carbon dioxide, you're breathing in right now and you're fine, right? So it does matter how many atoms you have in a covalent bond as well too, those fixed proportions. So we're going to look at these naming rules, but we are going to look at different naming rules for different compounds. So we're going to require separate naming rules for ionic and for covalent bonds. The other thing that you're going to need before we look too closely is you're going to need a periodic table. So if you don't have your periodic table with you on your course website, so I'm going to go to our course website, you always have a periodic table available. So you've got your course website here. I'm going to scroll down a little bit, and on your right-hand side here, you've always got your periodic table. So please make sure that you have your periodic table in front of you, whether it's a paper copy or whether it's this copy that I gave you here that's taking forever to load. It's coming, I promise. There it is. So you're going to need your periodic table just to make sure that we are confirming the type of atom, and we're also going to need charges from here as well too. Now that we have our periodic table, we can look at our first set of naming rules. So our first set of naming rules, we're going to be looking at binary compounds. So in this first video, we're just going to be looking at binary compounds. This is again what you did in grade 10, and we're going to save polyatomic for the next video. So a binary compound, what binary means is it means two. So a binary compound is composed of just two different types of atoms bound together. We're going to be using what we call the IUPAC rules. What does IUPAC stand for, you ask? International Union of Pure and Applied Chemistry. No one ever wants to say that, so we just call it IUPAC. Essentially what IUPAC is IUPAC is like the chemistry bosses. They come up with all the rules. So we don't want to come up with one naming system in Canada and then have a totally different naming system in Germany and then different again in Australia. So what IUPAC does is it makes sure there's consistency between chemists. So IUPAC rules are what all chemists follow. That's what we're going to be learning in grade 11, and grade 12 is just the IUPAC rules for chemistry. So the first type of compound we're going to look at molecular binary compounds. Now, molecular compounds are any compounds that have a covalent bond. So we're going to be looking at things that have covalent bonds. We're going to be looking at two nonmetals bound together. So molecular compounds use prefixes. You have seen these prefixes before. You did see them before in grade 10. Don't expect you to remember them, so that's why I'm showing them to you again now. So prefixes essentially tell you how many atoms are present. If there's only one atom, we say mono. If there's two, we say di. If there's three, tri. 4, tetra. 5, penta. 6, hexa. 7, hepta. 8, octa. 9, nona. 10, deca. So you actually might have seen these outside of chemistry. For example, in math, when you have a figure that's four-sided, we call it a tetrahedral. Anything that is eight-sided is an octagon. Anything that's six-sided is a hexagon. So you might have actually seen these prefixes before, and you're going to see them again in grade 12 chemistry. So I know it kind of sucks having to memorize them right now. There's really no shortcut for me to teach you for that, but know that memorizing them now, you're going to use them later, so it makes it easier. So we're going to go ahead and we're just going to dive right in. The easiest way to start naming compounds is to just look at naming compounds. And as we go through, I'm just going to show you a couple exceptions as they come up. So when naming a compound, again, I can't say this enough, the most important thing is to decide what type of compound it is. So I get it, CO2 is under the subheading molecular. So we're going to assume it's molecular, but we always want to double check. So to tell if it is a molecular compound, we're looking for two nonmetals. So just a reminder, on your periodic table, nonmetals are on this side of the staircase here. So anything on the right-hand side of this little black line here, this is going to be your nonmetals. So I see carbon, I see oxygen, they're both nonmetals. So that means we are dealing with a molecular compound. That means we are going to be using prefixes. So to use prefixes, the first thing that you want to do is you want to actually go through and tell me what the first element is. So C stands for carbon. If you didn't know that, use your periodic table. You don't have to have it memorized. So carbon, and then you are going to go ahead and you're going to tell me how many carbons I have. Well, I only count one carbon because I don't see any numbers there. So the prefix for one is mono. So it should be monocarbon, right? Not technically. This is our first exception. I wanted to show you the first exception. So the prefix mono, oh, I meant to highlight that. Let's erase this. There we go. The prefix mono is only used to indicate the number of atoms on the second element in the chemical formula. So essentially, we never use mono on the first element. We only use mono on the second element. So this is the first element. It's mono, so we're not going to say it. If it was di, if it was tri. If it was tetra, you would have to tell me. The only time we don't use anything on the first compound is if it's mono. This is mono, so we're not going to use it. So we're just going to call it carbon. Now we're going to take a look at my second element. My second element is oxygen. So I'm going to call it ox. And you might remember this from grade 10. When we're naming things, we always drop the ending of the element and we put 3 letters. Those 3 letters are I. Ox, I. Hopefully this is bringing back memories. So we're going to call this carbon oxide. And then you also have to report how many oxygens we have. So here I've got 2 oxygens. I know it's 2 because there's a little 2 next to the O. So I'm going to go ahead, I'm going to take a look at my chart, and 2 means di. So I'm going to put the di right in front here. So we are going to call this carbon dioxide. I'm sure this whole time you've been screaming at the screen because you know CO2 is carbon dioxide. I started with an easy one that you've seen before because I wanted to show you some of those rules. So we're going to go ahead. We're going to try the next one. We're going to try CO. So our first thing that we have to do is we're going to make sure that C and O are nonmetals. So we're going to come to the periodic table here. They are. We actually just checked that for the last one, right? So we do have nonmetals. So we're going to, oh, there I am. We're going to go ahead and we're going to name the first element. First element is carbon. Now, how many carbons do I have? 1. But remember, we don't use mono on that first one. So we don't have to use mono on that first one. We can go ahead and we can proceed right to the second one. So the second element is oxygen. So again, we're going to call it oxide. Drop the ending and put that IDE. You do have to tell me on the second one how many atoms it is. So here we have 1 oxygen. I'm going to go ahead. 1 is mono, so I'm going to call this mono oxide. Now here's another kind of tricky thing that we do in chemistry. This here, if you take a look at it, that says monoxide. That's really weird. We wouldn't call it monoxide. So usually when there's 2 letters that are the same side by side, what we do is we drop one of them. So I have 2 letters that are side by side. So what I'm going to do is I'm going to drop one of these O's here, and I'm actually just going to call this monoxide. So we're going to call CO carbon monoxide. I'm going to do one with you now, and then I want you to pause the video and try to challenge yourself, and you're going to try the last one on your own. So CCl4, we're going to check our periodic table. We are going to make sure that they're both nonmetals. They are. So we're going to go ahead and we're going to report what C means. C means carbon. How many C's do I have? I have 1. Well, since it's 1 and it's a first element, I don't have to use the word mono. So I'm going to go right to the next element. The next element is Cl. That stands for chlorine. So I'm not going to call it chlorine. I'm going to call it chloride because I always use that IDE ending. And I have to figure out how many 4 is. So I'm going to go to my chart. I'm going to look at 4. And 4 stands for tetra. So I'm going to call it tetrachloride. Altogether, this is going to be carbon tetrachloride. So I want you to pause the video now, and I want you to try the last one on your own. I want you to try P2H4 and see if you know how to do it. You're back. So we're going to take a look at P2H4. So P, phosphorus, is a nonmetal. Hydrogen, even though it's on the left-hand side of the table, is still a nonmetal. Tricky, don't fall for that. So both phosphorus and hydrogen are considered to be nonmetals. So P stands for phosphorus. So I'm going to go ahead and write phosphorus. How many do I have? I have 2. So remember, mono only doesn't count for the first one. Everything else counts for the first one. So here I would want to include the word di, di meaning 2. So diphosphorus. And then my next element is hydrogen. Remember, we dropped the ending though, so we're just going to call it hydride. Sounds weird, but it's right, I promise. Hydride. And then how many hydrogens do you have? You have 4. So we would call that tetrahydride. This big long name would be diphosphorus tetrahydride. Okay, so naming, not that bad. Now we're going to go ahead and we are going to work on writing the chemical formula. So we're going to work from the name to the chemical formula, whereas before we were working from the chemical formula to the name. So molecular binary compounds are written by writing the symbol of the element followed directly by the subscript indicating the number of atoms. Subscripts are not reduced. So essentially all you're reporting is what you see. Don't overthink it. Don't try to reduce stuff here. You're literally just telling me how many you have. So carbon disulfide. So the first thing I need to do is I need to remind myself what the chemical symbol for carbon is. The chemical symbol for carbon is C. Now I don't see any prefix here. The only reason I would have no prefix is because it's mono. So I can just leave C the way that it is. Disulfide. So sulfide stands for the element sulfur. So this can kind of be the tricky part, is you got to interpret a little bit. Remember, it's going to have that "ide" ending on it. So you kind of want to look at this part here and use that as a clue to figure out what your element is on the periodic table. So here I'm going to be looking for sulfur. The chemical formula for sulfur is S. And then di, I want to use that prefix to tell how many atoms I have. So I'm going to take a look at my chart, and di is 2. So I'm going to go ahead and write my subscript here, 2. Now note that I wrote it like a subscript. You do not want to write it like this. That's not right. You do not want to write it like this. That's also not right. Those bigger, we call this big number here a coefficient. Coefficients actually mean something else in chemistry. We'll get to that in unit 2. So you have to be really, really careful here that you are using what we call subscripts, and subscripts are those little numbers that follow afterwards. Let's try the next one together, diphosphorus pentasulfide. So we're going to look at the first element, and the first element is phosphorus. So if I take a look at the periodic table, phosphorus is represented by a P. Now I want to use the prefix to tell me how many phosphoruses I have. The prefix di means 2, so I have 2 phosphorus atoms. Pentasulfide, well, we've already figured out that sulfide is sulfur, so S. And penta, I'm going to check my chart here because that's one we haven't seen yet. Penta means 5. So here we're going to go ahead and do P2S5. That's going to be your formula for pentasulfide. I want you to go ahead. I want you to pause the video and I want you to try the last one on your own. You're back. So hopefully you figured out that phosphorus is again P and tetra means 4. Oxide means oxygen, and dec is 10. So my formula here would be P4O10. Two things I want to point out. I did not reduce these numbers. So I understand 2 will divide into both of those. Don't reduce them. That's not what you do in molecular compounds. So you want to make sure that you're keeping those the same. The other thing I want to point out is I didn't call it deca oxide. I had 2 vowels together, so I went ahead and I dropped the A to just say dec oxide. So you're going to see that a lot. Anytime that you have 2 vowels together, you're going to go ahead, you're going to drop the A, and you're going to leave the other vowel there. Tetraphosphorus dec oxide. So that's it. That's molecular compounds. That's not too bad, right? So what we're going to do now is we are going to go ahead and we are going to look at how to name ionic compounds. So remember, ionic compounds, we're dealing with a metal and a non-metal. So I want to remind you on the periodic table where your metals are. So metals are on the left-hand side of the periodic table. So anything on the left-hand side of your staircase, and non-metals are over on this side. So we are going to be looking at metals and non-metals combining to form ionic compounds. And ionic compounds, of course, have different naming rules. So ionic compounds are always written by listing the positive ion first. Your positive ion is actually always going to be your metal. So you always want to list your metal first. Here's the really nice thing about that. If you read left to right, which is most Canadians do, that's how we teach in Canada to read, is left to right. If you read left to right, the metal's always going to appear first anyways. So if you're looking at the periodic table, the metal's going to appear first anyways. So you always want to keep the metal first and the non-metal second. So metal ion is going to come first. Positive ion is going to come first. and the negative is going to come later. We're still going to be using subscripts, and those subscripts are going to be telling you how many atoms are present. However, determining how many atoms are present is a little bit trickier in ionic compounds. We do not use the prefixes. What we do is we use charges to ensure charge balance. So to ensure charge balance, each of the charge of the atom is going to be crossed over. That sounds tricky. I guarantee you the first time that we do it, you're going to remember doing this in grade 10. Before I show you charging or crossing over, I want to go back to your periodic table because in this case, you are going to have to know your charges of ions. So I know I've covered this in another video before, but I'm going to show you again because it's really important here now. You need to know what the charges of the ions are in each of their categories. So you need to know that anything in category 1 has a charge of +1. If you have a paper copy of your periodic table, I would write that down on your periodic table. You're always going to need to know that. Anything in group 2 has a charge of +2 because it's got 2 valence electrons. Anything in group 3 has a charge of +3. Group 4 actually isn't going to look at ionic compounds. Anything in group 4 is usually going to be molecular compounds, so we don't have to worry about that. Anything in this column here is going to have a charge of -3. Anything over here is going to have a charge of -2. And anything over here is going to have a charge of -1. So if you haven't already written those down, I would go ahead and write them down now, or hopefully you have it committed to memory, because you are going to have to kind of know the charges like the back of your hand as we go into ionic compounds now, because that's how you are going to determine these subscripts. So let's go back here and let's show you with our first example what I mean by crossing over. So again, we always want to make sure we're dealing with the right type of compound. Here we're looking at barium chloride. So on your periodic table, make sure that you now have a metal and a nonmetal because we're looking at ionic compounds. Ionic compounds are a metal and a nonmetal. Barium is indeed the metal. So you can see it's written first, and chlorine is the nonmetal, it's written second. So for ionic compounds, what I like to do is I actually call it rough work. So I like to actually write out what the ions are. So for example, barium, the symbol for barium is Ba. And if you look at barium on the periodic table, it's in the second group. So barium in the second group means that it's going to have a charge of 2+. So let's rewrite this so you can see it. I'm actually going to write a 2+ up at the top here. Now again, notice that I'm writing my charge as a superscript. So the charge for barium, we're writing up at the top here. A superscript in chemistry means charge. So you do not want to write the charge of barium down here. You do not want to write the charge of barium over here. All of those positions mean different things in chemistry. So you always want to write the charge as a superscript, as a small number at the top. So barium has a charge of 2+. Chlorine, Cl, has a charge of 1-. So I'm just going to put a minus right here. Now we're going to go ahead and we are going to record what our elements are. So barium, Ba, chlorine, Cl. Now in order to determine what my subscripts, that was right, my subscripts are here, what I'm going to do is I'm going to cross over my charges. So essentially this charge here, this 2, is going to come next to chlorine. So I'm going to take that 2 and I'm going to write it next to chlorine. And this 1 here is going to come next to barium. Well, we actually don't have to write a 1, so I'm not going to write anything here. Notice that the actual positive or negative does not get written. So all we cross over is the number, not the positive, not the negative. Essentially, this is a shortcut for us to ensure charge balance. So ionic compounds don't have a charge. They always have to have a charge equal to 0. So if barium has a charge of 2 positive, I'm going to need 2 chlorines each with a charge of -1 in order to balance that out, in order to have charge balance. So barium has a charge of 2 plus. I need 2 chlorines, 2 negatives to cancel out that 2 positive in order to equal 0. So essentially, by crossing over, what you're doing is you're ensuring charge balance. You're figuring out that each one barium is going to need to have 2 chlorines in order to balance it out. I don't want to have to think about this every time. I don't want to have to sketch this in my margin every time. So essentially crossing over allows you to skip this step and figure out exactly how many atoms are needed in order to balance your charges. So let's take a look at the next one, sodium sulfide. So I'm going to start with my rough work. Sodium is my metal. So it's got a symbol of Na. It's in the first column on the periodic table, so it's Na1+. Sulfur is S. It's in the 16th column on the periodic table, so it's got a charge of 2 negative. I'm going to go ahead and I'm going to write NaS over here, and now I'm going to cross over my charges to see what my subscripts are. So I'm going to have this 1 come down here. Remember, we never have to write 1, so I can just leave that the way that it is. And I'm going to have this 2 come over here. That means that next to sodium, I would have a 2 written right there. So my chemical formula for sodium sulfide would be Na2S. Let's try potassium carbide. So this is a fun one. Remember how I said carbon wasn't going to be in one? Sometimes they are. So potassium carbide is going to have a charge of it's going to have a symbol of K, and it's going to have a charge of +1, so K plus. And carbon is going to have a symbol of C. Carbon is over here on the periodic table. So if it does form an ionic compound, normally it doesn't, but if it does, I'm trying to show you an example. It's in the 14th column. So anything in the 14th column has 4 valence electrons. So it is going to have a charge of 4. So anything that's in this column here is going to have a charge of 4. So we're going to use 4 as the charge for carbon in this case. So carbon, we would have as a charge of 4 negative. We're going to go ahead, we're going to do that crossover rule. So this is going to come down here. That means that potassium's number 1 is going to go next to carbon. We don't have to write a 1 though. And then this 4 is going to come down here. So that means that next to K, we're going to have a 4 written. I want you to now try to pause the video, and I want you to see if you can figure out the next one. And I'm going to take it up with you in just 1 second. You're back. So magnesium oxide. Magnesium has a charge of 2, so 2 plus. Oxygen has a charge of 2 minus. So we're going to go ahead and we're going to cross these charges over. So I'm going to write this MgO. And this 2 is going to come down here. So I have a 2 written here. And this 2 is going to come down here. So I'm going to write a 2 here. And that's it, right? Some of you that really remember grade 10 are like yelling at the screen right now. This is one of our kind of little exceptions that we have to look at. So essentially, any time that we can reduce numbers in ionic compounds, we do. What I mean by reduce numbers is if we can actually reduce the subscripts to a lower number. So here I have a 2, here I have a 2. So since those are both 2, they can be divided by 2. This would reduce to MgO. If it was Mg2O4, then it would reduce to MgO2. So you want to look out and you want to see anytime that you reduce, you do. This is actually the correct formula for magnesium oxide. I'm going to show you why really quickly. Remember that this is all about charge balance. So magnesium has a charge of 2 plus. Oxygen has a charge of 2 negative. So 2 plus and 2 negative actually show charge balance. I only need 1 magnesium and 1 oxygen in order to have charge balance. So this formula here, actually not correct. MgO is our correct one. So that's something that you want to keep in the back of your mind. It's kind of one of those additional rules. So chemical formulas are to be reduced whenever possible. So that's all stuff that you covered in grade 10. Now we're going to throw one kind of new thing at you. This is going to be the little bit of grade 11 chemistry. So we're going to add to these rules, and we're going to talk about something that's called a peroxide. So you already heard me mention at the beginning of the note, I'd use the word hydrogen peroxide. What a peroxide is, it's a binary compound that contains one more oxygen than the most common oxide. So essentially, it's one more oxygen than you would expect to have based off the crossing over rule. So I'm going to show you what this looks like. Let's take a look at sodium oxide. So sodium oxide, if I was naming this like a regular binary compound, sodium would have a charge of Na+, oxygen would have a charge of O2 negative. So we have Na, we have O, we cross over our charges, so this 1 comes next to the oxygen. I don't have to write a 1. This 2 is going to come next to the sodium, so I would go ahead and write a 2 here. So when I'm writing my ionic compound for sodium oxide, I call it Na2O. Now a peroxide has one more oxygen than I would expect. So if I was looking at sodium peroxide, I expect to have Na2O. So one more oxygen, adding one additional oxygen to that would be NaO2. So the chemical formula for sodium peroxide is NaO2. Peroxides, anytime that you have the word peroxide, you actually don't reduce it. So this formula is in fact correct, just like H2O2 is correct for hydrogen peroxide. We don't reduce this number. So potassium oxide then, my symbol for potassium, K+, my symbol for oxygen, O2. So if I cross these values over, I'm going to have K2O. So in order to write potassium oxide then, I want to add one more oxygen to my typical formula. So instead of having K2O, I'm going to have K2O. I'm going to add one more oxygen to that, K2O2. So peroxides are kind of one of those tricky ones. It's new, but it's not that hard. All you're doing is you're adding one oxygen to what you would expect to see. All right, we are going to now visit something that you again did in grade 10, and we are going to look at what we called in grade 10 multivalent. So multivalent is anything that's in this part. Let me get my pointer. Anything that's in this part of the periodic table here. So multivalent metals are these metals that don't fit into the categories that we labeled before. So multivalent metals are anything in here. Now a multivalent metal, a lot of people ask me in grade 10 how I know for sure something is a multivalent metal, and it's a really great question. We didn't really cover it in grade 10. I want to show you something now. So I've zoomed on the periodic table, and I'm going to help you to identify how something is a multivalent metal. So we want to take a look at silver, and I'm going to, let me underline here. Get my underline tool. I'm going to get my highlight tool actually. So silver, see this, see this little +1 here on silver? This is the potential oxidation state of silver. So it's kind of like saying the same thing as charge. So silver here, we only have one oxidation state listed. That's essentially telling you the charge of silver. The charge of silver is 1. So anything that's in that box that we haven't covered yet, we actually are told the charges here. So silver is 1. I'm going to take a look at its neighbor though, cadmium here. Cadmium has a +2, so the charge of cadmium is +2. Now let's go down here to gold. Gold has both a +1 and a +3 listed. Since there's 2 numbers listed here, this is an example of a multivalent metal. It's something that actually would have multiple charges. Mercury has 2 possible charges, 1 and 2. Thallium has 2 possible charges, 1 and 3. So a multivalent metal is anything that actually has more than one possible charge. So if it's in that weird box of like group 13 to, or sorry, group 3 to like group 13-ish, you want to take a look at what we call the oxidation states, and you can actually see if there's only 1, then you know what the charge is. If there's 2, you have a multivalent metal. Now here's the challenge with the multivalent metal. How do I know what charge to use? So for example, example, for gold, how do I know if I'm using the number 1 or the number 3? I can't be sure. So we actually have to adapt a little bit of an exception for the multivalent metals. You did this in grade 10. We're going to remind you how to do it now. So when you're writing the chemical name of the compound, we're going to use the oxidation state of the metallic element listed using a Roman numeral. So essentially, we're going to list the charge using a Roman numeral, or the charge is going to be given to us using a Roman numeral. So let's take a look and see what that looks like. So our first example, we're going to do copper bromide. The symbol for copper, Cu. And if I take a look at copper on the periodic table, let's go back here. Am I still zoomed in? I am. So, will it let me do this? Maybe. Nope. Oh, it's because I'm still erasing things. Okay, let's zoom out a little bit. Excellent. So I want to go ahead and I want to find copper. I can see copper right here. And if you take a look at those little small oxidation numbers there, copper has a 1 and a 2. Copper has 2 possible oxidation states. It's a multivalent metal. So here, what you're being told is you're actually being told the charge of copper. This Roman numeral here, this 2, is telling you that this is copper 2. So the charge actually specifically has to be told to you in order to understand what the charge is, because you have 2 possibilities. Bromine is that nonmetal, so bromine always has the same charge, -1. Now it follows the exact same rules for ionic. So we're going to go ahead, we're going to write Cu, we're going to write Br, and we're going to do that crossing over. So this 2 is going to come down here, and this 1 is going to come down here, but of course we don't have to write a 1. Let's now take a look at what copper 1 bromide would look like. So copper 1 bromide, again, the charge is being given to me. It's a 1+. Bromine is going to be that negative. So copper 1 bromine would just be CuBr. I want you to try the next two on your own. So pause the video, see if you can figure it out. We're going to check. You're back. So iron 3 sulfide. So to write iron 3 sulfide, iron, the symbol for iron, Fe, and 3, you've been told the charge, 3+. Sulfide is S, and the charge on sulfur is 2, so we're going to go ahead and write that 2 there. Now we're going to cross over our charges. So this 3 from iron is going to come next to sulfur, and this 2 from sulfur is going to go next to iron. The chemical formula for iron 3 sulfide would be Fe2S3. This is a tricky one for multiple reasons, but I love it. This is something that I'd love to ask you on an assignment. So mercury 2 oxide, the chemical symbol for mercury is Hg. And here you've been told the charge of 2, so it's going to be 2+. Oxygen has a charge of 2-. So we're going to go ahead and we are going to cross over those charges. So this 2 is going to come down here. This 2 is going to come down here. So Hg2O2. Remember, this is still an ionic compound. So if you ever get the chance to reduce, you do. So if you told me Hg2O2 on a test or an assignment, it's part marks, because in reality, mercury 2 oxide is HgO. We reduce when we can. So that's not too bad. We're just going to look at it in reverse now. So we're going to take a look at when naming ionic compounds, what we do. So when we're naming ionic compounds, we again list the metallic element first. No prefixes are used. You use the "ide" ending. Let's take a look and let's see if we can figure these out. So we're going to work in reverse now, and we're going to go ahead and we're going to name. So we are not using prefixes at all. We're using the "ide" ending, and we always list the element first. Now, the one thing that you do want to look out for is you want to look out for those multivalent metals, because if you do come across a multivalent metal, you do have to give it to me in Roman numerals. So let's take a look at sodium bromide. Sodium is in fact a metal, and sodium is not a multivalent metal. It only has 1 charge. So in order to name this, all we would have to do is write the word sodium, and instead of writing bromine, I use that ending "ide" bromide. Now let's take a look at ZNO. So Zn is zinc. If you take a look at it, zinc is not a multivalent metal. Don't fall for it. So if you actually look on the periodic table, and if you find zinc, zinc only has that charge of 2+. It only has one number there. So if zinc only has one number, it's not multivalent, it doesn't have multiple charges. You don't need to tell me the Roman numerals. So I'm just going to go ahead, I'm going to call this zinc, and I'm going to call oxygen oxide, and the name for this is going to be zinc oxide. AlF3. So Al stands for aluminum. So I would want to go ahead and write aluminum here. F stands for fluorine. So I would call this fluoride. Now remember, this is ionic compounds, so we don't care about prefixes. So you don't want to tell me that's aluminum trifluoride. That is incorrect. We do not use prefixes for ionic compounds. You just list what you see. If the binary compound contains a metallic element with more than one oxidation state, so if you are dealing with a multivalent metal, you want to make sure that you tell me what the charge is in Roman numerals. So for example, HGS. So if we find Hg mercury on the periodic table, you can see it right here. It's got two numbers listed down there. It's got a 1 and it's got a 2 listed. Since it has those two numbers listed, then we are dealing with a multivalent metal in this case. So we have to go ahead and we're going to name mercury, and we're going to name sulfide, but you also have to tell me the charge. Now here's the tricky part for the charge. You need to actually kind of think about this to figure it out. This is probably one of the harder ones I can give you, but I like a challenge, right? So here you got to do a little bit of logic. So let's think about what the charge of the other ion would be. We know the charge of sulfur, and sulfur is going to be 2 negative, right? Not a plus, negative. So sulfur is going to be 2 negative. Now, I don't see a 2 listed over here. I don't see a 2 listed next to mercury when there should be based off the crossing over rule. The only reason there wouldn't be a 2 there is if mercury had the same charge and was also 2+. So in this case, we know mercury must be 2+ in order to cancel out that 2 negative. This would be mercury 2 sulfide. What would mercury 1 sulfide look like? Mercury 1 sulfide would look like this. We'd have our Hg2S. So sulfur again would have that charge of 2 negative, and then that means mercury must have that charge of 1 positive. So you kind of got to think about it to figure out what your charge is. One last thing that we want to talk about, and these are going to be some of those kind of weird grade 11 things. So there's a couple of things that act kind of strange with ionic compounds. The first one is the compounds that contain hydrogen. So if you have a compound that contains hydrogen, I want to point out where it is on the periodic table. So we are going to remind you that hydrogen on the periodic table, zoom out. Oh, too much, come back. Hydrogen on the periodic table is over here. So even though it's arranged with the metal side, it is technically a nonmetal. So hydrogen is considered to be a nonmetal, even it's over here on the metal side. But it acts kind of weird because it can kind of act as a metal sometimes. So hydrogen actually kind of has its own naming rules. So when you have a compound containing hydrogen, if hydrogen is first, prefixes are not used. So essentially, if hydrogen is first, it acts like an ionic compound. So if hydrogen is first, it actually is forming an ion. It's actually losing that ion to that nonmetal. So it's acting as an ionic compound. So in this case, hydrogen is first, so we're not going to use prefixes. So all we have to do is write what we see. So for example, hydrogen and chlorine, I'm naming this like an ionic compound. So the first element, hydrogen. Second element is chlorine. I'm going to call that chloride. The next one that we look at here, H2S. So hydrogen is first, sulfur is second. So I'm going to go ahead and I'm going to call hydrogen, because that's what it is. Sulfur is going to be called sulfide. I am not using prefixes because I'm treating this like an ionic compound, so I'm not going to use a di. It's just going to be hydrogen sulfide. And finally, we have hydrogen first, bromine second. So I would go ahead and I would call that hydrogen bromide. So when hydrogen is first, you name it like an ionic compounds. Hydrogen can also form ions with anions with metals. So if hydrogen comes second, but it's formed with a metal, it's still going to be like an ionic compound. So here we've got hydrogen is second, but it's being combined with a metal. Well, we know that anything that combines with a metal is an ionic compound. So I'm again not using prefixes. So here I'm just going to write what I see, lithium. And if hydrogen is second, hydride. Or here I have sodium, so sodium. Hydrogen is second, hydride. Or here I have aluminum, so aluminum is first. Ooh. Hydrogen is second, so hydride. So hydrogen can actually have three different rules around it. Hydrogen can be first, and it's named as an ionic compound. Hydrogen can be second, combined with a metal, and it's an ionic compound. Or we looked at some at the beginning where hydrogen was second. It was with a non-metal, and that's named like a covalent compound. So hydrogen, you've got to be a little bit tricky. You have to think about where hydrogen is and also what it's bonded to. Last thing I want to show you in this video, because I'm trying to get you ready for the chemistry world. In the chemistry world, we sometimes have something called a classical naming system. So what a classical naming system is the IUPAC names are sometimes a mouthful. So some chemists have come up with a shorter name or a classical name. You're going to see this again when we talk about naming acids. So I don't want you to get to a chemistry lab and people are using a classical naming system and not IUPAC, and you don't know what anything means. So we're going to be looking at a classical naming system for copper here, because it's pretty common. So in the classical naming system, elements that have two oxidation states were differentiated using ic to indicate the higher oxidation state and us to indicate the lower oxidation state. So oftentimes in a lab, instead of seeing actual multivalent with the little Roman numerals, you sometimes see ic, and us as endings instead. So for example, we're going to look at cupric chloride and cuprous chloride. So we're going to go to copper. We're going to pull up copper over here because we know we're dealing with copper, right? Cupric and cuprous means copper, Cu. So we're going to zoom in on copper here, and we can see copper has two different oxidation states. Copper has an oxidation state of 1, and copper also has the oxidation state of 2. So in our classical naming system, oh, didn't mean to do that. Oh, geez. Go away. In our classical naming system, ic means the higher oxidation state. So remember, copper has two different oxidation states, +1 and +2. So ic must mean I'm dealing with copper 2. Ic means the higher number, so I'm dealing with copper 2. And then I would write this just like a regular ionic compound. So I'd have Cu, Cl. These are going to go ahead and cross over. This is going to cross over down here. And I would have CuCl2. Us means the lowest number, lower number. So that means I must be dealing with copper 1 in this case. So again, I have my crossover rule, and I would have CuCl. So that's a classical naming system. It's something that's a little bit more old school, but you actually see it in a lot of labs. In my chemical storeroom, nothing says copper 1 or copper 2. It all says cupric or cuprous. So it's something else that you might want to consider. Other than that, that is it for binary. I am very excited. So this is kind of part 1 of our lesson done. Now what we have to talk about is polyatomic. So I am going to ask you to join me for our next video. And in the next video, we are going to continue talking about naming compounds. It's still going to be a review of grade 10, but now we are going to look at polyatomic compounds. So I'm going to go back to this screen. I'm going to stop sharing, and we'll see you in the next video.